Okay, hello everybody, good afternoon. If the gentleman having a chat in the aisle would stop chatting and sit down, we could start the session. I can also name you individually, like Gory, Jörg, Thomas. Please sit down. Okay, welcome everybody. This is MAPRG. We should also turn off the music at some point, or we just keep it today, I don't know. And somebody's running to tell them to turn off the music, perfect. Okay, there we go. Ah. You have to tune it down carefully, okay. Let's start. Welcome to MAPRG. So this is one of the research group meetings. We have a full but not like too packed agenda today, but I think a very good agenda. First of all, I show you the IPR text from the IETF, and that's somehow not aligned correctly. Oops. Okay, that should work. Yes, so there are also IPR things you have to consider, and that's written on the slide. And if you have not seen it yet, go and read it in the proceedings. This is the usual pointers to our charter, our mailing list, today's slide and remote participation that might be helpful for you at some point. Let me just take it out on the slide. Yeah, and then last time I presented a little bit of feedback we got from the IAB review, because every research group has once in a time, or like from time to time actually, a review with the IAB, and we had a good discussion, and we also had a discussion about what we did so far and what we could change or where we could improve. A couple things came up and I presented this last time. So one thing we did change this time is that I did a little bit of spamming. So I tried to send a pointer to those working groups which might be interested in the talks we have here today. And I got no complaints, but I got a little bit of positive feedback, so that seems to be useful. People told me I was not aware of this. Thank you for sending it, so I will continue that. The other thing we have discussed with the IAB, or came up from the IAB, was that this research group has many nice talks which are interesting for a lot of people in and outside the IETF, and there is a possibility to write blog posts. And we already had one blog post from people presenting their work here. And if you have a presentation MAPRG, or also other interesting measurement results, you might be interested in writing an IETF blog post as well. If you would like to do that, you can contact me, or you can contact Greg Wood directly. But I think I've seen a lot of presentations here that definitely were very interesting and could give a nice blog talk post. The third point on here, where the bullet point is actually missing somehow, was the thing that I brought up last time, and I didn't get a lot of feedback, so I would like to ask it again. And that's like, is this group interested in like only consuming measurement results, or is this group also interested in being a venue for sharing data and collecting data? And if so, if there's this interest, what to do about it? Like, how can we get the people in here to bring their data? And which data do you want to see? And one simple idea was to like pushing everybody who gives a talk a little bit more on the side of making their data available and make it easy to at least find the data for the talks that we have here. And I don't see anybody rushing to the mic, so it's kind of a no. Okay, but that's an answer as well. Okay, and oh, somebody in the remote queue.
Hello, everyone. So I would be the one to say, yeah, actually, we should consider doing this. There was some work that we did in the MOMI project on building sort of referenceable databases of intermediate measurement results that I could possibly talk about in Prague, or we could talk about in a hackathon in Prague. As to looking for, some sort of sets of intermediate measurement results that might make sense to share over a platform like that. So there was this repeatability in measurement dog stool workshop, I think about 3 weeks ago. And one of the things that came out of that was some people who have larger scale data collections were talking about what it would take to get their APIs together so that you could use essentially a single client for all of those particular things. So maybe I could propose a talk on the state of these things in Prague, and then we could speak forward from there.
Okay, thank you. That sounds like a good plan to me. Okay, and then the last point on this slide brings me also to the next slide. One proposal was also to interact with the community closer, for example, by having a MAPRG-focused hackathon table. And especially Dave, my co-author, co-chair, really liked this idea. And he will push this idea for, he's not here today, unfortunately, but he will push this idea for the next meeting in Prague. And the current two measurement ideas he brought up was one, to check the current state of ECN, because there was a hackathon table at IETF101. So this is like kind of a continuous measurement work, which would be nice to do. And the other one he's interested in is measuring DNS. And there's also a related paper at IMC, actually, which is a link here. If you're interested in these topics, watch out for a hackathon project at the next meeting, or if you have more topics around measurements that you would like to hack on at the next time, please talk to us.
Tom Jones. I support the idea of a hackathon table. I would sit there. Comcast before have offered virtual machines on their DOCSIS backbone for the hackathon. And this probably needs to be organized in advance because it wasn't getting utilization, but it would be a good thing for a platform to have for measurements.
Okay, so you have a contact there?
Charles?
Okay, that's easy. Okay, cool. Yeah, we will also announce this on the mailing list, so if you watch out a little bit, you shouldn't miss it. Okay, and talking about IMC, this is like one of the reasons why Dave is not here, because the IMC, the Internet Measurement Conference, was last week in Boston. So he went there and I'm here. And what he did is that we talked a little bit about it and he enjoyed the meeting a lot. It was a good meeting. It was a lot of people, packed agenda, more papers than previously. And he put the effort into pick out some of the papers that might be most interesting for this audience, so you have it easier to find the stuff that might impact your work directly, while the other presentations were probably also very interesting. So check out the agenda.
Hey, Chris Wood. There was a paper I don't believe I see in here on coming of age in TLS by Kenny Patterson and some others that might be useful for.
Yeah, but we have a presentation on that. That's even better.
I know, but just like putting it on this would be good.
Oh, it's even there, okay. Okay, and that's our agenda today. We have a quick heads up talk, and then we actually have 5 presentations, and the last 2 are actually IMC papers that were presented last week in Boston and are now here for you, brand new basically, and we go ahead and we start with Tobias. Except you have any questions, or I don't think we do agenda bashing here, actually. We don't have time for that. There's no box.
Do we have a clicker? Hey, so welcome. This is together with Dave, and it's about some things we found in our research on privacy on IPv6 scanning and IPv6 deployment. And basically, we stumble a lot about EUI64 addresses. Actually, there's one error on there. RFC 4941 has by now been overruled, but I forgot to update the slides. And technically, the problem of having EUI64 addresses on the internet should be kind of solved. However, when we were looking at actual measurements out there, we found that, for example, if you do trace routes across the internet for V6, you find up to 45% of hosts responding with EUI64 addresses for ICMP time exceeded, which is A, quite a lot, but B, mostly CPEs. The other example we had actually in a work where we looked at how we can actually enumerate reverse DNS. We could actually track people walking across buildings when they were auto-populating their reverse DNS, because like 8 a.m. to 1 p.m. they were in building 1, then they had lunch, and then they were in building 2, and we were actually able to verify this over the website that these buildings exist. In addition, also the addressing practices in IPv6 can lead to, well, privacy implications, because now you can actually do things structuredly, so you have a lot less noise in there, which aids topology discovery. So, for example, in one of our works, we could discern the policy of .mil installation quite well accurately. There are 2 related publications. One has been at IMC, was I think also in the list Mira showed, from Dave, which is mostly around measuring IPv6 adoption, and where they found these 45% of responses from EUI64 addresses. And then there's the paper where we, for example, found the building stuff together with Kevin Bergolta and some other people, which was at Security and Privacy this year. Our idea is to actually put up a draft in which we document what we find out there, in contrast to what we should find there. So we have a reference point for further measurement, something we can say like, okay, this is how it was in 2018, this is what it was in 2019, and continue working from there. This is basically a call for measurements and observations. So if you have anything which also falls in the context of IPv6 security and privacy implications, we would really like to hear your input. Even more so, we would like to hear your data sets. So if you have any of this, please drop us an email at dave@plonker.us and my funny institution mail address. And that's actually already the last slide. If there are no comments.
Yeah, thank you. Please engage with Dave and Tobias. No comment. Okay, then we just go ahead to the next longer presentation.
Hello, I'm Tom Jones. So, University of Aberdeen, we've been working on implementation of UDP Options. UDP Options adds transport options to UDP. It does this by taking advantage of the fact that when UDP is carried inside IP, there are two fields which describe the length of the UDP datagram. There is a length field in the UDP header, which describes the length of the UDP header and the data, and there's a length field in the IP payload, which is IP payload length, and normally these two numbers are the same. And so we can create surplus space after the UDP option, after the UDP datagram, by increasing the IP payload length while keeping the UDP length the same. We get a surplus area. In the surplus area, we can stick in transport options. And transport options look like this. And so we have some options for structuring with space and creating a checksum for the option space. And then the rest of the options are TLVs, where they have a type length and then a value they carry. And so we've been working on this for about a year. And at IETF, TSVWG in London back in March, I showed this slide as an extra slide about a potential issue we had with deployment. And there's a nice little subtle bug in here that we came across. When we were trying to send UDP datagrams from our host with options, we were getting malformed checksums. And so this is the indelayed checksum function for FreeBSD. This is called when you're not offloading checksums to hardware. And the issue here is that when we do the checksum, we always take the IP length, and then we use it to perform the checksum over the UDP datagram. And then we have the code below there, which handles the case where we have a UDP checksum, which is 0, where we invert all the bits. And you know, this is small, and it's actually quite straightforward. The conclusion from this was don't offload UDP checksums to hardware so they don't do this wrong, and then we'll fix it in code, and it'll be done. And great, you know, fixing FreeBSD, the IETF, making the internet better. Went to the pub. And of course, that hasn't really worked out. And so we've been doing measurements for UDP options for the last couple of months. And UDP options are fun to measure. There are no hosts on the internet yet which support UDP options, so we've had to come up with some other solutions. We have a tool called Mobile Tracebox Core. It's a continuation of a tool called Tracebox. It performs a traceroute style TTL ring search, and allows us to see where in the network packets are modified or dropped. And we've been using this for doing measurements, and we also find that UDP is quite difficult to measure. Unlike HTTP, where there's a big list of public services, UDP doesn't have such a diverse set of hosts that you can find lists for. We did manage to come up with host lists for Stun, DNS, and NTP. And even then, we still don't get a lot of results from these. Rafael Zulu, who developed the tool, figured out that you don't actually need a UDP service on a host to send UDP datagrams to it. And you can use the ICMP port unreachable message as an indication that the host is responding and receiving your datagram. And so we take the Alexa top 1 million list, we filter out the hosts which don't respond to this, and we get a larger set of hosts we can measure against. And so with this, we've done some measurements for UDP options, and they sort of look like this. This plot shows the chance of a path for each of these measurement types to pass a UDP options datagram end to end. You might see that there's about a 50% chance of failure. And it's not very good, and it's not very promising for UDP options. And we thought about this, and we were trying to figure out why. And Ron Bonica brought this up. You know, when the checksum's wrong for a packet, a lot of stateful boxes drop the packet because they should. They shouldn't feed more broken stuff into the internet. But these packets are being incorrectly detected as broken, and why is this? And so we interrogated this, and we figured out some pathologies for what's going on. Our favorite pathology is that everything's treated correctly and it works. And then sort of in descending order of frequency, we find the checksum on the UDP datagram is being done on the full IP payload length. And this is the same as the bug we saw in FreeBSD. And so this issue that we thought would be easy to solve turns out to be a big chunk of the failures we find. And then the next two cases are weird. We see the full payload checksum, but the pseudo header is created using the length in the UDP header. And then we see the correct checksum length performed, but with a pseudo header created from the IP length header. We see UDP options payload being passed as long as the option space only contains zeros. And while that's cool, we're not really sure how to use that. And then we see hard checks by middle boxes where they compare the IP payload length to UDP length. And this one, we don't think we can solve. So today I'd like to introduce the CCO. The CCO is an option for UDP options. It uses a modified pseudo header and the checksum across the UDP options space. And it creates a checksum which, when you calculate the checksum across the UDP datagram and the UDP options space, you get the same checksum as you would get if you correctly calculated the UDP checksum. This is magic. We see a huge increase in the number of paths which will successfully pass traffic. But better than that, it actually works through CPE. So Ruda Barak at the University of Oslo has a test bed he's made out of the strangest things he can find in flea markets. He goes to secondhand shops and he picks up whatever he can. He has a test bed and he ran his tests through 23 of these devices. And at first pass, 17 of the 23 would pass UDP options, but 6 would drop it. When we add in the CCO, all 23 devices pass it. Great. Okay, and so this is what we're proposing. We have a draft on this. We'd love it if you read the draft, and we'd love if you passed on comments about this. And if you send them to the authors directly or to TSVWG, we'd love to hear what you think. Questions?
Thank you. I think I heard a lot of support. But given there are no questions, we go to the next talk.
Okay, hello everyone. My name is Nicolas Kuhn. I'm presenting work we have been doing with all these people listed underneath. And there's something I need to make clear before I start is we have not been working on IETF Quick, but more on the Google Quick implementation. Basically, why we wanted to work on it is because first, Quick is here already. So this is a chart lots of you may know. So that's the guys from Aaron working on these things. So they have a website where you can actually extract these figures quite easily for your talks. And so we just picked a point randomly, not so randomly, but when actually Quick was 25% of the traffic. So it's based on the Maui traces. So this is one of the main reasons why we wanted to work on it, but also because we as SATCOM, we split end-to-end connections with TCP. So basically, every TCP connection is split in 3 independent TCP connections. And why do we do that? Basically, when you look at the underneath picture, we have 3 different websites with different characteristics. The 3 pages are downloaded with IW10, so initial congestion of 10, or initial congestion of window of 60, and we just split the connection with the PEP. We just keep the cubic inside the PEP. We don't do any specific optimization, and just by splitting TCP, we have the time needed to download the web page. So basically, that's why in the SATCOM industry, we will go on splitting TCP connection, but the problem is that we can't split Quick at the moment. So that's why we work on it. That is a slide to show basically some analysis of Quick and SATCOM. Basically, what could be good for Earth is that we have problems with making TCP fast open when we split TCP connections. So the zero RTT handshake thing is very interesting for us. Problem is we may not be able to adapt the congestion control. Good thing is we can support with that lots of new congestion control versions, And without PEPs, our ground segments would be a lot cheaper. And also that would not having, we don't put PEPs because we want to split, but because we have to. And basically that's a big problem for us because we have to follow all the trends in end-to-end to actually support the good innovations, and that's a cost for us. Also, one of the threats we have at the moment, but that's more for an operator point of view, is when you have all different kind of traffic with different characteristics being under the same port, it's getting complicated to do some quality of service management for the different needs of the different applications. And also threats that we have, and that I will show later on, is that we have some issues with the end user quality of experience. So basically the question we have is Quick doing any better than split TCP for SATCOM public access? Gori already mentioned on the mic during whatever talk that, I don't remember when it was this week, but basically that it's sure that split TCP is doing better, but we just wanted to make simple measurements to measure by how much it's doing better. So our testbed, so these are following different questions we had. So how can we trust our Quick experiments? We can't replicate any Quick implementation available today because we don't have all the smart congestion controls that may be embedded in it. So the good and easy way for us to doing so is basically using Google servers. So we just get different targets, one being a huge object and the other one being smaller pages. Another thing we did to have an actual end-user perception is that we have in CNES public SATCOM accesses. So we just have a terminal and we connect we have public accesses. So we connect our laptop to the terminal, satellite terminal, and go to the different web pages. So the good thing is we have real end-user experience. But then the problem we have, and I will be back on that later, on multiple moments, is that there are lots of things happening, lots of operator tooling that we don't actually understand. Also, because there are lots of things we don't understand, we know some TCP versions embedded in PEPs for SATCOM, but sometimes in this case we don't. So basically there's some unknown congestion control on the satellite link, probably Neutrino-based, doing lots of strange AMD optimizations. And on Google servers, we may have BBR, but we cannot be sure of it. So, and then also, then something we need to mention is we had a problem to find a good browser. So we had to, basically, we've taken the Chromium browser with or without the Quick option enabled. So we understand that our experiments are just cannot be extended to lots of cases. We just wanted to point out some end user experience. Also, we are a small community, so we want to make everything we do available to anyone. So all the scripts that run on whatever VM, so using any VM and connecting to a server, enabling Quick, you can reproduce all the results we have done and all the experiments we have. So feel free to use it. And that is just a slide to explain a little bit better how we made our experiments. So we focus on W3C metrics to measure the page loading time and the time to restart. And we compare those two. We make different web pages downloads, and then we purge the browser profile. And so basically we use Selenium to automate our measurements. For the results, we show this kind of diagrams. We don't have lots of plots, but still it shows the disparity and how the measures are distributed. Basically, for the first load, we often and always have the same page loading time. That is, for the first part, I will focus on the big page we download. And basically, what we observed is that in Chromium implementation, we always start with a TCP connection. So the first load is the same. So in blue, no Quick, and in red, with Quick. But the problem is that for the second and the third load, as soon as the Quick knows to be available, with Chrome Quick, we use Quick, and this ends up with page loading time that is doubled for this page. So the first reason of our question is Quick doing any better than splitted TCP for large page on satellite? It's not the case. So this is, to be more sure, the CDF of with some French words, but that's the CDF. And but basically, we show that we have two completely independent CDFs, so we are quite sure about what we are showing here. To better understand, we have tried to come up with some sequence number view. So this is the sequence number reception in byte, and a function of the time since the connect starts. So the first triangle is when we actually start to download data, and the second triangle on the top is when we finish to download the page. So we will be back to that after, but the first bytes come before with Quick, but not so much. And also what we can see is basically if we look at the derivative, when you look at the ramp up, we can see that with the PEP we have a very high and stable throughput. We get up to speed directly because we know our conditions. With Quick, Quick congestion control doesn't know. Google Quick's congestion control doesn't know that we are on a satellite link. So basically it takes it a while to actually come up to the good and available boundaries. This is the part of the things we don't understand. Basically, if we look at, but because we want to be honest, and so when we look at the different loads, we see a huge disparity in the Chrome no Quick page downloading time. In basically everything in the response starts, what's happening there is strange. That might be due to the channel capacity, the way the access is done. So all these layer 2 things that are happening. So we don't actually know, and we couldn't dig into the details. We see some strange 2 phases if you look at the CDFs and the blue part. Basically, half of the measurements have a slow time to response starts, and the other half is very high. So maybe something is lost and retransmitted. We don't actually know. If we look at the small page, the thing is basically Quick is doing better. I don't know how much time left I have. It's fine, but basically we can see that the fact that we have the first bytes of data that come faster with Quick is a huge gain in this case. And so again, there are lots of things we don't understand. We just wanted to report some results and share the code we have, that anyone who wants to replace it with any kind of other accesses can take the code and try it out. So as a conclusion, for small files, Quick is winning even on the satellite link because we have very first data bytes that arrive earlier. For large files, splitted TCP wins. And the big issue is how to get up to speed with Quick in this case. So the paper is here, and we are here to have any discussions on it. So what you want to jump in now, or that's my last slide? Okay. Basically, what we plan to do next is investigate on how we can send relevant informations to the Quick server, such as the initial congestion window to use, some congestion control parameters. We are not sure about which of them we want to send, but we want to have them to have the possibility to do so if we cannot split the connection. And so long term, if we wait for the IETF Quick release to make more concrete proposals on congestion control changes. So, thank you.
Ian Sweat, Google. Thanks for the talk. I think I'm sorry, number one. I'm also not surprised. This is one of the cases where I think it's very, very hard to do end-to-end as well as the split TCP approach. And the core issue, at least based on not as much talking with you, but with some other satellite uppers like John Border, is it's not uncommon on satellite that the ideal congestion window end-to-end is in the thousands of packets, is my understanding. So say it's like 3,000 to 5,000, maybe even 10,000 packets. That's a pretty large number by internet standards, at least in my experience. So our numbers indicate that a median congestion window for a typical connection is something more like 20 to 40 for most users. So you're 2 orders of magnitude off the typical user. You combine that with the longer RTT, and slow start is going to take a while to fix that. So I'm very interested to see what you might come up with to to make this situation better. I think there might be some things on the server side we could potentially do, but yeah, I mean, this is sort of the nature of, this is one of those cases where end-to-end is actually worse because you just have a network that's so different from like the typical network, and connections are relatively short-lived typically. But thanks.
For example, for the small solutions we may have, we have already measurements on just increasing a lot the initial congestion window helps. So if we can say just pace it, our RTT is 60 and pace a very large congestion window, and that helps a lot already. We're not aiming for something that we know will be impossible, not possible, but we will try to find some small tricks that would help us a lot.
Yeah, I think if we did one IW1000, that would probably help you guys a lot. But probably would probably make a bunch of people super grumpy.
But if you pace it, that's okay.
Well, yeah, we always pace in TCP and Quick at Google. But yeah.
Wes Herdeker, ISI. So like 15 plus years ago, which means that the data is no longer valid, but I actually looked into studying UDP versus TCP, long before Quick. And one of the conclusions that I came to, and specifically I was looking at satellite links and things like that, which at the time were really lossy, like 33%, lossy. And I suspect that that's gotten better, and my knowledge of the situation has gotten worse on the other hand. Did you look into lossy networks and how that affected this type of result as well? Or?
For the moment, we are working on geo satellites fixed access, where the loss ratio is lower than in LTE and Wi-Fi. We have very high precision. We have no loss. We have a quasi error-free transmission. But then when it comes to satellite constellations or mobile users, that's not the same. We have bursts of losses. So the pattern of losses is not the same depending on, but we are focusing on geo broadband access, internet accesses.
Right. One of the things that I found when I did my study, again, 15 years ago, so data is no longer valid, but was that TCP falls over completely and fails at like 33% loss or so, whereas UDP eventually does win if you keep retrying. But
some value eventually. Yes, some value. Thanks for this work. I'm glad to see satellites are still as problematic as they were 25 years ago. So I have a comment and a question. I guess the comment is when you start looking at the large initial windows, I think it would be really useful to also try to take some measurements of the effects that those large initial windows have on low latency traffic, like on the other side of the hop. Right, because you're going to be very unresponsive to congestion events then, and I think that trying to not only document sort of the performance increase that you'll see over the satellite link, but also look at like how bad are you making it for everybody else who's sharing the network on the other side would be, that's going to be part of the story, right?
For the large initial congestion window, we can increase it a lot if we pace it. It's just that if you send one packet every 5 milliseconds, during 500 milliseconds, you have already sent a lot of data without including too much burst in the network. So we're not asking, that's just one thing we work on. It's true that we can't have the same initial congestion window as in LTE. But then, and for the second point of latency sensitive traffic, we have end users with SLA contracts and requirements for latency sensitive traffic. So we have quality of service management where we actually prioritize this kind of traffic such as it has low latency. And I mean, it is not affected by, the problem then in how your congestion control is affected by the quality of service management you have underneath. But that's a generic topic, not only specific to our case, I believe.
Sure. And then the question that I had, going to your environment, I think that you, when you were talking about your test environment, it looked like you said that on the satellite link, you weren't actually sure whether they were running some sort of TCP optimization. They were running your UDP packets, your quick packets over some TCP optimization. So do you know for a fact that there is some TCP running in here, or were you just saying that you were uncertain?
We know that some industrials do actually base their optimization on TCP.
Yeah, but I'm asking about the results that you showed. Do you know for the measurements that you made whether they were doing that or not? I think that's be good to know that to try to understand, because that's certainly going to affect the performance.
Yeah, sure. But one of the black box effects when we make trial measurements. Thank you.
Hi there, Bob Briscoe. I just thought I'd come up. I don't think it's a controversial point. I just wanted to correct the people who are saying that this is a problem with satellite. It's actually a canary in the cage for what will be the problem as links get faster, because bandwidth delay product is about bandwidth as well as delay.
Yeah, we are not just a corner case.
We would have like 2-3 more minutes if you want to show the tooling slides.
So basically, since we have more time, and that's something slightly different. I didn't want to make too much noise about it, but we are here. And basically, we have we are a public institute, so we believe a lot in open source. So we have this tool that is basically experimental. Basically, we use lots of open source tools available to orchestrate results. We have lots of simple unit jobs so that we don't care anymore about how you actually do an iPerf 3, what version of iPerf you're using. At least we're sure about what we're doing once and don't focus about it anymore. So basically, there are information on the website. What we do with it at the moment is from network metrology. We have lots of multipass scenarios where basically we think for educational, at least, very interesting. But also these scenarios we have here, it would become just a click, and you will run the test. And for example, one of the things we wanted to do is we found this very interesting work on experimental BBR congestion control experiments done by KIT Institute in Germany. We wanted to check out if this issue is actually real in SATCOM when you have BBR stealing the whole capacity that QBT could have had. And basically, now that we have implemented that, you just have, if you want, I'm not speaking about opening having a common TCP evaluation suite document in the IETF, but it's just that we are having tools to experiment lots of things around TCP fairness. And so whenever we have a new congestion control we want to try out, to just put it in this box, and we have lots of scenarios that would run. And we think it's useful for the community because we always complain about how to evaluate the fairness or performance of different congestion controls. So if you're interested, drop us an email, or we are here, and we'd be happy to give more information about it.
Okay, thank you very much.
Thank you.
Hello. Probably you really hate it when someone is presenting somebody else's work because they don't know deep in detail what it is about. And this is one of those cases. I will be presenting on behalf of two colleagues, Roberto Moravito and Zaccaria Larusi. The topic is vehicular communications and how different application layer protocols may affect them. You have all the information there on the reference below. This was presented in the IEEE CSCN conference this year. So let's start with the purpose. So the main idea is to see if MQTT, CoAP, or HTTP, depending on the vehicular network, might affect the performance. Also, depending on whether we use edge or cloud to provide the service, whether also that may affect the performance. We use vanilla MQTT, also CoAP and HTTP. That means that it's MQTT over TCP with the QoS of 2. That affects also the results you will see later on. And with HTTP, we do not use QUIC, which probably would have shown much better results. So it's plain MQTT TCP, CoAP UDP, and HTTP TCP as well. In the scenario, it's rather simple. So we have a vehicle, a car with an onboard unit that is contacting an InnoDP, a base station. Relatively close to the base station, we have the edge server that is provisioning with the same services as in the cloud. We do not modify the base station in any way, or we don't have the edge server co-located with the InnoDP. That's what I'm trying to say. So that shouldn't affect the latency in any way. And these are the two scenarios. In theory, of course, the latency and the throughput should be better on the edge. The setup is done in Finland. So we have, on future work, we would like also to check vehicle-to-vehicle communication as well. So we will need more edge entities. At the moment, we have only one edge entity, which is located nearby the path of the vehicle. The car will connect to the edge entity when it's nearby, and it will connect to the cloud through the normal mobile operator when it's not. The data center is in Lund, in Sweden, about 850 kilometers away. And yeah, so the two cases is the vehicle is close to the edge or is not close to the edge, and is transmitting all the time. So the participating entities. So we have, let's start with the data center. So as I said, that's in Lund. We run OpenStack, and inside we have a VM with a set of software and protocols that are required to send and receive data. Payload size, rather small, about 11 kilobytes. Not so small in the IoT scenario, of course, but relatively small for other environments. The edge entity is Dell server T5500, 15 gigabytes of RAM, pretty powerful. So there is the terminology, there is something called a roadside unit that normally would be like much less powerful than that. So in that case, we are also providing more capabilities there. Yeah, as I mentioned, there is no local breakout between the base station and the edge server. So we are running it on the normal network infrastructure in Finland, and the same thing goes for the mobile. We use the mobile operator DNA, and no specific tweaks there. The onboard unit is a Raspberry Pi 3 running Raspbian, and again running co-op MQTT and HTTP. It's connected to a 6-pub shield, and we have a 4G LTE module, and it's transmitting there. So very simple setup: edge unit, edge server, onboard unit, and the cloud side. Sorry. So we have this testbed in order to test multiple things later on in the future as well. At the moment, so far, we have tested the comparison between the cloud and the edge, and whether using the edge actually really does improve latency and throughput. Also, as I will continue later on, we do a comparison of the various application layer protocols. But in the future, we will also look into a bit larger size payloads and how does the edge operate in those environments. We haven't finished the empirical evaluation there. And we also test with other radio interfaces other than 4G. So locally, we would like to use Wi-Fi, and for vehicle-to-vehicle Wi-Fi 802.11.p. Moreover, later on also, we will test with other application layer protocol modifications, just like we did for MQTT QoS settings. So other than what I already mentioned, we check on other factors like the vehicle speed, the number of clients, and again the QoS. So I'm kind of repeating the same thing. The background. All right, I didn't check this slide before, but here you can see basically the setup we have for HTTP, co-op, and MQTT. So the architecture of co-op is client to server, RESTful type of interaction. The co-op server is running on the device, the co-op client on the cloud, although in practice is device to device, so kind of a bit of peer-to-peer setup. It has a bit of a larger header size compared with HTTP, compared with MQTT. The paradigm of communication between MQTT, HTTP, and co-op is a bit different. MQTT is designed for PubSub type of communication, although co-op also supports the same kind of pattern with observe option, and HTTP is also RESTful. Then on the semantics, so basically, yeah, there are different methods to do similar operations. We do the basic one, so get, post, put, delete, basic operations on resources on the devices. And similarly, basic operations when it comes to the MQTT side. So connect, disconnect, publish, subscribe, and so on. There is a bit of a larger handshake if you are using TCP that is not contemplated here. Yeah, so that will be basically it. On the QoS side, as I mentioned, well, I can go later on it, but basically QoS 0 has no delivery guarantee. QoS 1 is basically that at least the message has arrived one, and QoS 2 there is a very high guarantees that the message has arrived one time. but it implies that there is a four messages overhead. And that's pretty much it. I mean, this is well known already. For the evaluation, so the setup is on the protocol side, we're running Mosquito, which is very well known. It has a broker, it has a client server. It has a benchmark tool that allows you to edit the QoS, to edit throughput, to do modifications on the broker as well. In the case of HTTP, we run simple Apache. Plain HTTP plus TCP Apache, and the benchmark tool that they provide. And in the case of CoAP, libcoap, which is a C-based implementation. You can instantiate as many clients and servers as you want, and it has a benchmarking tool as well. So as far as empirical results go, so for the vehicle speed, sadly, we couldn't test at really high speeds. It was only the variability was only from 30 to 50 kilometers because of the speed limitations. So obviously there was no correlation. I believe probably, I mean, we will need to run this in another place where the speed limits are a bit higher. But at least you can see some interesting results as far as performance goes. In which basically the CoAP outperforms in terms of, so let's explain the graph a bit. On the left side, you have the throughput in messages per second, and on the right side, you have the latency in milliseconds. And in the bottom, you can see how the edge and the cloud perform in each of the cases. So you can see there that the performance when it comes to CoAP, yes?
Jamie, just a question. I mean, you mentioned an MQTT, which quality level you use. 2. Yes, but you don't say what you use in CoAP. I mean, what do you mean? Neither the method nor the reliability level.
We use confirmable messages, and that's it. Confirmable messages. There was not, the acknowledgement was not confirmable. Okay. So it would be matching, I would say, quality of service 1, but we don't really have that terminology in CoAP. Actually, that would be something interesting for further work as well, to see how the CoAP could match this kind of quality of service terminology as well. Essentially, you could send a confirmable acknowledgement so that you receive the confirmation back and you know that it has been received only one time. So, yeah, so again, CoAP over UDP with the observe option, with the confirmable option on, so that you receive the acknowledgement. Yeah, where was I? Yeah, so the throughput was about, in the edge case for CoAP, 25 messages per second, which was almost, in one of the cases, almost twice as the messages per second for HTTP and MQTT. MQTT performed a bit better than HTTP. And in terms of latency, again, CoAP did outperform the other two as well, greatly. But again, in retrospect, I think if it had been HTTP 2 over QUIC and MQTT with QoS of 1, it would have been different. We did the analysis MQTT with QoS of 1. You will see later. CoAP still outperforms, but the difference is not as dramatic as in this case. And again, as it was expected, the cloud also had a bit of a higher latency and a bit of a lower throughput. So no surprises here. And then the next one, we did, so assuming that you have this kind of onboard unit and this kind of vehicle connected to the internet, you may have different type of services. So you have an infotainment system with video, you may have some telemetry being sent, so they have different requirements. So we wanted to test not those requirements in particular, but having multiple clients connected at the same time and see how the performance varies. So again, on the left side, the throughput, on the right side, the latency. And as we increase the number of clients, the throughput greatly decreases, especially in the case of HTTP, so that the 10th client, actually the throughput is almost 1/3 of the first one. In the case of CoAP, the throughput was much higher and actually had a very good efficiency because it was only 10% difference between the first and the last client. Latency-wise, it was pretty high for HTTP. Again, I believe the fact that we were using TCP has something to do with that. I'm not sure why actually. But anyway, it's something to look into. But again, the latency was much better for, well, slightly better for co-op than for MQTT, and definitely much better for both of them than for HTTP. In the next one, so the QoS, for those who don't know what the MQTT QoS is, essentially is a way to ensure that the message delivery has been made. We didn't use QoS of 0 because essentially you don't have, it's best effort, so you don't have any guarantees whatsoever. We could have used QoS of 1, and we did. I will continue on that to be a bit more fair, since we were using co-op UDP with plain confirmable messages and no equivalent guarantee of delivery. QoS of 2, actually, I think it was designed for satellite communications, actually. So it has quite a lot of message transmission, and therefore it performs a bit worse. But it's the safest, obviously. So this was the results. The throughput greatly was increased when using QoS of 1. So QoS of 2 greatly reduces the throughput, and conversely, same thing happens with the latency. Still, the results, if you remember from the previous slide, so here the throughput for QoS of 1 was about 17 messages per second. In the case of co-op, it was 24, 25 messages per second. So still, co-op outperforms MQTT even with QoS of 1. Yes.
So is the QoS1 then using UDP, or is this also running?
No, TCP, everything TCP. We could have used MQTT SN, and that would be for also for
So
future.
how can it be unreliable if you have TCP underneath?
Sorry?
How can it be unreliable if you have TCP underneath?
It's not, I mean, it's the application layer, I suppose, like the MQTT layer needs to confirm the message delivery. But I mean, if any other MQTT expert.
I guess it's a little bit apple with pears, because of the TCP underneath. I mean, we already offline discussed, we have made a similar study with MQTT SN over UDP, and co-op and also ICN protocols. It was just published 2 months ago at the ICN conference. And what we saw is that actually, if you put in confirmable messages or reliability layers, then the MQTT and the co-op are pretty similar.
Yeah.
They're pretty similar. If you switch, if you use QoS 0 for MQTT and you have an
No confirmable message.
you have an unsaturated link. So if you actually have capacity on the link, then this is actually the quickest protocol.
Yeah.
I mean, on the other hand, what we see is, I mean, we were using IoT scenarios with 15.4 links. What we actually see is that the confirmable layers in both protocols basically fail if you have link saturations.
Yeah. All right. That's interesting.
Can you send a pointer to the paper on the
I
mail
can
list?
do. Yeah.
Thank you.
Yeah, we didn't have any specifics on the 4G. I mean, we were using 4G and LTE, so it's a completely different case than 15.4, but that probably is affected as well. And again, we didn't use MQTT SN, which could have been also interesting. Actually, we got a lot of feedback when preparing this on how we could improve later on, having more tests and more variations. Again, like it was very small size messages that could affect the way HTTP perform. It seems that co-op did outperform over MQTT when it comes to QoS of 1 and 2, and HTTP, of course. Both co-op and MQTT perform HTTP in this case, both in the case of throughput and latency. Yeah, and basically, like we confirm also that the edge case performs better than the cloud case. That is interesting, actually, because we have started a bit comparing for larger size payloads, and the preliminary results show that the cloud performs a bit worse than the edge performs a bit worse than the cloud. We haven't figured out what the reason could be, but that also for future work. In fact, the question? Or, all right. So for future work, we have we would like to work with larger size payloads or workloads, and also maybe test on some streaming cases like IPTV, for example, Yesterday, in fact, in Core, we had a very interesting presentation on that for videos with very low frame rate. So it's not full-fledged video streaming, but a bit of a lower quality one with H.264 encoding. Then we would also like to test other security mechanisms, OSCORE, for example, so for application layer security, and see if that affects the throughput as well. And other network interfaces, as I mentioned at the beginning. When we have a couple more edge entities, we will also test the vehicular communication and see how the placement of the edge entity, the distance to the UE affects. And in the base case scenario, we will even modify a base station to offer an added value service there. And that's pretty much it. Thanks. Yeah, please go ahead.
Yes, so Florin Babuescu, Broadcom. Few questions regarding the access. I understand that you are experimenting on a 4G LTE base station. Okay. Can you detail how much bandwidth the base station has? 5 megahertz, 20 megahertz?
This is the case. Like
okay.
Yeah, I'm so sorry, but it's probably, if it's, I will offline. I can check with you. That question.
Is it a single base station? In other words, the whole track, it's under the coverage of the same and in a good signal strength?
Yeah. And anyway, it will be the same signal strength for all of the three cases. It was the same environment.
I'm talking in the context of the speed test.
The speed test. Well, I mean, I think it was barely a speed test because the difference was 20 kilometers.
No, I understand. But the problem is that the vehicle is moving.
Yeah.
The signal strengths, practically the RSRP, RSRQ, which details may change during the experiment part.
I believe this was only one. I mean, the location actually is a bit almost rural in nature. It's not like a very highly populated environment that you have multiple base stations. You may have Pico, Femto, and so on.
I understand. I believe but again, the base station signal strength, the frequency of operations, the bandwidth that you have has direct implication actually what you can do.
Correct.
And the last question regarding the access would be, what is the maximum number of HARC processes that you have? HARC retransmissions. So on the access, practically you have a error correction mechanism in which a frame may be sent multiple times with error correction schemes. I'm asking because at least in the latency numbers that you put it there are very ideal. So I would expect at least in the context that your vehicle is moving, those latencies may change. What I say is that at a minimum you're going to have 8 milliseconds. That will going to be the overall latency on a transmission.
So the latency did change depending on the speed, but as you can see, it was not like, so on the right side you have this 10 milliseconds from in the edge case, it was about from the picture 10 milliseconds difference based on worst case, and in the cloud's case maybe like 20.
To give you an example, on a typical operator, on a data radio bearer, we would expect to have on an average 4 or 5 retransmissions, which are going to make the access to be like at least 40-50 milliseconds overall latency for the access. So that is, so if you look at your numbers on the edge, practically that number represents only the overall access. And the last question it is, do you make a request for data or do you go with semi-persistent connections? In semi-persistent connection, practically you are granted periodically. This is something like we do for voice. For example, every 20 milliseconds, you have a grant and you do not need to make further requests to the scheduler on the node B.
We didn't, I mean, so let me think about it for a second. So on the Raspberry Pi 3, we were running plain Mosquito. We didn't do any modifications of how the scheduler on the
it's part of the node B scheduler and it's part of the terminal modem, how the two negotiates and what type of communication we're going to do. So that's why I'm asking if you have any specific details.
No, I mean, I believe there was no specific modifications on how the communication to the I don't think there were specific modifications below IP layer, to be more precise. It was the same setup for all of them, plain out-of-the-box setup. We didn't do any modifications also on the edge side. We didn't do a local breakout between the edge server and the base station. It was normal network connection. Thanks.
Marco Coelho. Clarifying question about the workload. Did I understand it correctly that you are using repeating small message exchanges continuously?
Yeah, 11 kilobytes of size, I believe. Yes.
Okay. And then about the MQTT and HTTP, are they using persistent TCP connection, or are they opening a new TCP connection for each message exchange?
I do not know. I would be guessing the answer if I would say
because the results seem to be showing that you are opening a new connection for each message, because there is the performance difference is roughly twice. So you get 2 round trips for the TCP based stuff and just 1 round trip for the co-op based.
Okay, that would explain actually why the results for HTTP were not that great actually. Yeah, I mean we can
that
also
seems to be like
that could be a very good explanation actually.
Okay, thanks.
Thanks, Marco.
One question, quick question. How often did you repeat the measurement? Do you know that?
I think it was 5 times. This is in the paper. I have to. This is the case that, as I said, I'm not the author. I can check it, but I think it was 5 times, I believe. If I remember correctly, I can tell you as soon as I sit there and I check it.
Okay, thank you. So maybe you can come back with a short update next time.
Yeah, I think. Yeah, I think next time probably we'll have maybe the quick case and vehicle to vehicle seem to be the most interesting. And if it is about simple tweaks of each of the protocols, we can also do that.
Thank you.
Thank you. Thanks.
So hello everybody. This talk is about a measurement study that we did on the upcoming deployment of certificate transparency. And a short version of this talk was already presented last week at ACM IMC. This joint work with Quirin, Oliver, Theo, Johanna, Lexi, Georg, Ralf, and Thomas. And yeah, so the rise of certificate transparency. Before I get into the details, let's briefly recap what CT certificate transparency is and why we need it. So, I mean, if you're an owner of a name, you can get a certificate. Unfortunately, anyone else can ask for a certificate for the same name, and if something was wrong, he actually or she gets a certificate. And the problem is that the name owner does not have any chance to verify if another certificate for his or her name exists. So how to solve this problem? What is one option is that you actually make all existing certificates publicly available. You store all of the certificates in a log server, and these repositories can be fetched from a monitoring node, and then the name owner can check if another certificate for his or her name exists. And this is basically the idea of CT, certificate transparency, to provide a transparency into the issued certificates, and for this it uses a public append-only log to record the certificates. So that is an approach that was, there's an RFC out of this, and was implemented on the browser side as well as on the repository side. Mainly driven by Google, and there was the question is a little bit how to enforce now the deployment of these CTs. And this is easy if you have control about the client, the browser more or less. You just enforce that every certificate that is delivered by a server is also available in the CT log. And there was a deadline in April 30, where Google said in Chrome, every certificate that is issued after April 30 and is not in the certificate transparency log will trigger a warning in the web browser. So, and from this point of view, CTs, I mean, there might be some chance that they are, will experience some deployment. And this is something that we want to analyze here, and also the implications of having CTs deployed. So there are 2 basic questions around this new approach. One is, does CT introduce new dependencies? and to which extent, because you have the log server infrastructure. This log server infrastructure is operated by multiple companies, and you would expect that the CE who published the certificate would do this not only in one log server operated by a single company, but hopefully across several companies, just to prevent concentration on a single point of failure. And the second question that comes along with the deployment of CT is what do we lose or gain in addition to checking the CT logs, the certificates. Why? Because what is CT actually doing? It is exposing names, right? And having access to names in an easily way to search, you can think about, for example, to find something like malicious domain names, phishing domain names, but also you can think about that attackers leverage this public repository to find victims. This is these both questions we try to answer in our measurement study. So let's first look on the increase of deployment of CT. What you see here is on the x-axis the time, and on the y-axis the number of log entries in the CT logs by different CT log operators. And the orange dashed line actually indicates April 30, so the date of time where Google Chrome gives you a warning if a certificate is not part of the CT log. What you see is that the number of log entries across the different log operators increase over time, and in particular, close to the deadline, there's a huge increase. Let's Encrypt was publishing several 100 million certificates. So there's an increase, there's deployment, and according to the public log servers, you also see that Let's Encrypt dominates more or less the certificate ecosystem. So there's a strong rise. Now the question is, are these CAs who issue certificates distributed certificates over many CT logs? So do they care about reliability? And what you see here is on the x-axis are the most popular CAs, Let's Encrypt, DigiSet, and so on. And on the y-axis, you see the log servers. So a company might even operate several log servers. And the color in this heat map indicates the number of log entries per log server per CA. And what you would expect is that the color per column actually is somehow homogeneous, which would indicate that a CA is using several log operators. And unfortunately, this is not the case. What you see is, for example, that Let's Encrypt, first of all, dominates the market that we saw already, but also focus on two log operators. Let's Encrypt is publishing their certificates mainly at Google and Cloudflare. And this is also valid for other CAs. Some of the log operators are very rarely used, so you have a very sparse matrix here. So overall, the CT ecosystem more or less relies on a few log servers instead of using all available log servers. This picture indicates some limitation in reliability, and should be changed actually in the future. So now let's think about the implications on CTs, because CT is exposing names. So the first question that you can ask is, can we use CT to actually identify malicious names and domain names? And with malicious domain names, we mean phishing domain names. So what we are doing is we fetch all publicly available CT logs from all log servers, and then exclude for 5 popular services, which are Apple, PayPal, Hotmail, Google, and eBay, exclude all valid domain names, something like apple.com, and then do a pattern matching that use the valid domain name and looks for domain names that includes this valid domain name somewhere else in the name, something like appleid.apple.com - something. So this is a typical phishing domain name. And by doing this, simple, very, very simple pattern matching algorithm without any fancy machine learning or something like this. We come up with 176,000 potential phishing domain names, right? And most of the domain names actually relate to Apple, 63,000, 58,000 to PayPal, and some more to Microsoft, Google, and eBay. And then we actually also try to get some ground truth on whether these domain names has been used for malicious activities, and we did contact several certs, and actually got confirmation that some of these phishing domain names have been used for malicious activities. So to conclude this, yes, CT can be used to find malicious domain names quite easily, and you can think about deploying a system that analyzes the logs and warns you about suspicious names, for example. So that's a good. Now the question is about the ugly and the bad. And this is related to the question whether CT can be used by attackers to find victims. And what we did is first, we asked the question, can we, based on the data that is in the CT, construct domain names that are not, has not been known before? And what we did is we extracted all subdomain labels for all CT log certificates, something like def for def.io, and then artificially generated full qualified domain names in the way that we use the subdomain labels and combine this with suffix labels. We ignored .com, .net, .org because then you would get too many domain names anyway. And then we, after we created these artificial names, we verified whether there is whether these are valid domain names in the sense that there's an A record available. And based on this, we actually ended up with 18.8 million full qualified domain names based on this simple mechanism. And compared to other publicly available domain lists, something like from the Sonar measurement project, we have found 17 million more domain names. So yes, CT can help attackers easily to find previously unknown domain names. And think about as soon as you have a domain name and an A record, you can much more easily target the victim instead of, for example, scanning blindly the IP address space. And another question related to this is, can we also find, does this data somehow leak private information? And what we here did is that we analyzed the names and verified, looked into the ranked the subdomain labels according to the number of appearances. And what you see here is that the number of subdomain labels and the number of domain names where they are included. And among the top 10 subdomain labels, you find something like WebDisk, cPanel, and WHM, which might indicate a name that is used, or an NTOS, a service that is used for remote control, which, if you think about an attacker who, for example, does a password attack, might help to identify the victims. So the last question that we try to answer is if an attacker actually, having the knowledge of the CT logs, having a DNS name, actually misused this name. So which basically means does resolves the A record or quad A record for this name, and then also does a scanning on the corresponding IP address. And for this, we actually introduced the CT honeypot, and the CT honeypot consists of 4 components. This is first, we create a pseudo-random number DNS name, so a name that is hard to guess based on hash value. Then we then we created a certificate belonging to this hard to guess DNS name, published it in the CT logs. And then we monitored the logs on the authoritative DNS server on the one hand, and we also captured all traffic, our incoming traffic on the corresponding IP address that relates to the artificial domain name. And then try to correlate requests on the DNS for this name and the incoming data on the IP endhost. And as an attacker might easily use publicly recursive DNS servers to hide their source address, we also inspect the extended DNS subnet field, which gives you an indication of the original stub resolver of the DNS request. So first, as soon as we publish the data, as soon as we publish the log, we saw DNS lookups for these hard-to-guess names in less than 1 minute. It depends a little bit, but I mean, we created 11 names. Was a little bit, details depend a little bit on the name, but more or less it was on average after 1 minute. And we also saw access on the IP address after 1 hour on the HTTPS port. And when you look up, I mean, dig a little bit more into metadata about this source address that does this DNS request or the scanning on the IP endhost, you did not find any additional meta information that might indicate or that you would actually create when you do, for example, a research measurement study, such as a recursive DNS entry or WHOIS data. Still, I mean, some of these requests actually belongs to monitoring systems. But what is much more interesting is that we also found one scanner that immediately after resolving the DNS name that was exposed by the CT log was also scanning 30 ports of the corresponding IP endhost. So this and tracking back the source IP address of the scanner to an autonomous system. Actually, this autonomous system is somehow well known for hosting DDoS servers. So this is there is some indications that actually CT is misused and can easily be misused by attackers to more easily find potential victims. So to sum up, so far this measurement study is based on data from April this year. The CT ecosystem is dominated by a few stakeholders. Most of the CAs are logging to just a few log servers operated by a few companies. CT might help to find malicious domains such as phishing domains by easily applying something like pattern matching. You can get much better data if you do much more sophisticated searching on this. On the downside, CT also helps attackers to much easily identify potential victims, either by constructing previously unknown domains or by doing targeted scanning on the domain names that are visible in the CT logs. If you are interested in more details, in the slide set, there's also the paper linked. Thank you.
So you continue these measurements, right?
Yes.
Did you have any thoughts on how to improve the system?
How to prove the system?
Improve.
Improve the system. I mean, yeah. I mean, if you think about the phishing domains, I mean, you can apply some machine learning algorithms. Yes. I mean, what is from my personal point of view, actually, is most interesting is this analysis of the CT honeypot, right? That you can correlate. You publish a certificate with a name. The name is immediately, the CT log is monitored. The name is resolved, and then you see a scan on the corresponding A record or quad A record. This is a little bit actually hard to maintain on a long term because you need to create again and again a new name. As soon as the name is published, you cannot, I mean, it will be cached somewhere, and then you cannot rely that the next requests are, I mean, based on the scan of the logs instead of getting this data somewhere else.
So are you still operating the honeypot? Or is it
No,
one
at the
term?
moment not. I mean, this honeypot stuff you can only do per name as a one-time shot, right? As you see one request, it's done. Armin?
So this is very interesting. Do I understand correctly that you were able to get an entire copy of the CT logs? It seems like you needed that.
Yeah. I mean,
does that seem like a good idea to you that one can acquire?
I mean, this is something that is. I mean, I gave you some arguments why this is not a good idea because you have attackers to find victims.
Yes.
But all of the log servers here on the left-hand side of these graphs provide you the data publicly, right? That's the idea of the whole CT, that an external person, why it is so slow, an external person can monitor the CT logs and find a certificate for a name that it should not belong to.
So, but it seems to me that if I understand the purpose of the logs, what you want to be able to do is look up a name that you already have, as opposed to get a copy of the logs and be able to pour through it and see what useful things you can do with the information.
Point is, I mean, to find a certificate that was incorrectly issued, you need to scan the whole log, right?
Okay. So let me phrase my question a little bit differently. Did you come up with any recommendations for how the system might change to become better?
No. That is, I mean, I think, these privacy concerns, for example, that relates to CT are not new, right? We just give measurements that this is not a theoretical concern. That is actually a concern, but we did not discuss ways to improve this.
Okay.
And yeah, personally, I'm not a big fan of this anyway, but this is because I think it's the wrong idea to solve the problem. But it's a different question.
This is Ulrich from IS. You need to scan the CT logs actually if somebody is submitting fake subdomains of your own domains. So it's not only the hosts you have that's easily detected, but somebody could just,
That's intrinsic to the system. And if it is a good idea or not, anyone can judge on their own. We gave some ideas why it's not a good idea. Yes.
Tommy Pauly, Apple. This is just kind of a funny comment. Thank you for sharing how many phishing domains you see under Apple as well. I'm pretty sure I've seen, a good half of those in text messages, so you know where they're going. Yes, we get quite a lot of these. So improvements in the area would be lovely.
Wes Herdeker, ISI. Good work, first off. It's an interesting study. Have you thought further on sort of next directions, to go, and in particular, measuring the effectiveness of certificate transparency? There's always been the debate of, is this helping, the big people, or, the mom and pop shops don't really get helped much kind of things because they're not looking to see if their domains are being misused, or are you actually able to measure are users actually being protected by this? That type of measurement, I don't think is easy to do, unfortunately. But have you thought about it at all?
Not so far, no.
Okay.
Dan Drutzer. Actually, I don't see why there is not a simple solution to this, because instead of you doing the scanning on the logs, the owners can do the scan. You just provide the information and they come back with the matching, rather than exposing everything. It seems to me like the flaw on.
Yeah, but this is something you're running in circle, because you're arguing that there's an authentication between the name owner and the log server. But this is something similar to that the name owner, that only the name owner should get a certificate for the name, right? And if such mistakes never happens, then we would not need the CT log. And as similar as you can have a mistake in issuing the certificate, you probably can also have a mistake by the authentication of the main owner and the CT logs. I'm not sure if this really helps. I think that's the same issue, right?
Ulrich from IS again. Have you checked on your honeypot if there were really attacks? Or just access? So
it was a low interaction honeypot. So it was basically, it was not doing any handshake with the attacker, But I think there is some evidence that, I mean, someone who first requests a name and then does a scanning on multiple ports, that this is not a legitimate access, actually. But there was no high interaction honeypot deployed, only low interaction honeypot.
Thank you. Yes. You want to try that?
Shall we go? Okay, well, thanks everyone for staying. This is pretty late in the day, long day. But this is a measurement study that I did with a group of researchers from various different places to study OCSP and OCSP must stable. So what is that? A lot of you may know HTTPS is the basis of browsing the web. It's HTTP over TLS. Everybody here at the IETF knows this. Okay, so we've got a lot of time, but I'll try to rush through the obvious details and get to the meat of the study. But yeah, so when a browser connects to a website to securely communicate, the website introduces a private and public key pair to encrypt the channel, and just off the bat, there's no way for the browser to trust the website, so you bring a third-party certificate authority into the mix. So the website will send its public key to the CA and in return get back a certificate, and the certificate is signed by the CA's key, and this is what's presented with the public key to the browser. And this is the basis of the Web PKI. So the browser checks the certificate chain. The certificate is signed by an intermediate certificate, signed by a root certificate. That root certificate trusted by the browser, and bada bing, bada boom, secure communication on the internet, right? At least on the web. So what happens when a certificate is no longer valid? Say if the private key has been stolen by an attacker, then this attacker can then impersonate the website if they're, say, on path. And this is a bad thing. This is that's basically how it works. If the site doesn't realize that this compromise has happened, then there's not much they can do. But if they do realize that compromise has happened, they can talk to the certificate authority and tell the CA to revoke the certificate. So now when the browser receives a compromised certificate, it's the browser's responsibility to check to see if the certificate is revoked, and then essentially no longer trust this attacker. So there's several mechanisms that have been standardized for this: the CRL, Certificate Revocation List, and OCSP, which is a query protocol that we are going to be studying in this research. So browser checks, voila, it's not good. So how does the CRL work? This is sort of simple background here. A CRL is just a list of revoked certificate serial numbers, and the browser will periodically download this. It can this URL containing the CRL can either be embedded in the certificate, or it's something that the operating system repeatedly does for the certificate authority. And yeah, you just check to see that the certificate is not part of the CRL, and if it's not, if it is, then it's revoked. So this is not necessarily efficient. We've seen CRLs that can be up to 76 megabytes. After Heartbleed in particular, there were a lot of scaling issues with the CRL. So this is where OCSP comes in as a slightly more efficient protocol. So OCSP is more of a querying protocol. So when the certificate gets back from the website to the browser will specifically query a server that's stood up by the CA to say, is the certificate revoked or not? And they will respond with revoked, good, unknown, and this is valid for a specific time period. And If it's revoked, connection is closed. So what are, I guess, the challenges of this? Specifically, the OCSP responders, the CA needs to provide a service, a high availability service with low latency. So if you're going to be checking for blocking your connection on doing this remote HTTP connection, that might actually slow down your connection. So this is kind of a bad thing. It has to be low latency, and it also has privacy concerns as well. So this CA is not really involved in the user's connection to the website, but this communication reveals the traffic patterns of the browser. So this is not great. So this is where OCSP stapling comes in. This is why it was introduced, and the basic idea is very simple. The web server itself will do the certificate revocation check and obtain the OCSP response, and then include it in the TLS handshake if requested by the browser. So in this method, the website these OCSP responses are typically valid for 7 days or so. They can just fetch one for the site, put it in whenever the browser says, I support OCSP stapling, they get an OCSP response, can check the validity. So there's no additional latency, no blocking on random HTTP calls, and the CA is unable to track. So this is a pretty good thing compared to the standard OCSP mechanism. So what are the challenges here? So OCSP stapling doesn't solve all the problems with OCSP. One major problem is that clients will accept a certificate even if they're unable to check validation. So a lot of browsers have kind of made the optimization that revocation checking is really not worth the hassle. So specifically with OCSP checking, almost all browsers at this point, because of the latency hit, they just won't do it. So if they don't obtain an OCSP within a certain amount of time, then they'll consider this revocation check as, okay, this is just too much of a pain. We'll just consider it trusted. And so an attacker could potentially block this. And this is where the idea of OCSP must staple comes into play. This is a new X509 certificate extension. It's based on RFC 7633 TLS feature. It's essentially a flag in your certificate that says, if you understand this extension and you see the certificate and it does not come with an OCSP response, then consider it invalid. And so everything's essentially the same. There you go. It's this certificate cannot be used with a browser that understands OCSP must staple. So this is no additional latency, no privacy issues, no soft failure. This is just totally the high-level overview of the state of revocation online. So to support OCSP must staple, CA must include the must staple extension, run a reliable, error-free OCSP responder, where I guess we'll discuss that a little bit later what that means. And clients must also understand the extension, as well as present the request for OCSP. And if they see a certificate that does not follow this TLS feature, then they must refuse. So to support OCS must stable, web servers need to fetch and cache OCSP responses. They must configure the server to use OCSP stapling. And yeah, so there's these three components, and they all have certain properties and things that they must satisfy to have this ecosystem work. And that's what the study is measuring all these three pieces together. So generally, yeah, we're looking at the certificate authority side, we looked at the website side, and we looked at the browser side. So we were hoping to, in this measurement study, understand how close the web is to being ready for OCSP must stable, whether it's universal deployment or just even a small deployment, because there's currently very, very, very few certificates that have this property, somewhere around 10 or so in use, according to certificate transparency logs. All right, so let's look at the OCSP responders. The availability, validity, consistency with CRL. These are the things that we decided to study. So the methodology taken here was we used Census, which is an online scanning service. by the University of Michigan, which contains, say, at the time of the beginning, it's 100 million certificates or so. We picked 77 certificates inside of this that were valid for the next 30 days and support OCSP. And then we essentially tracked how from this group, we ended up having 536 unique OCSP responders. So of those 77 million, there were around 15,000 or so that had unique responders, and so we picked these 15,000 that correspond to these responders, and we set up a measurement client. So gathering these certificates, we would just do OCSP queries to the certificate OCSP server for each of these. Right, so in order to get a better sense of how this works globally, we deployed this in 6 different AWS regions, and it's, I mean, the reason for this is hard to know the exact status of OCSP responders and how they're configured worldwide. This is not the greatest, most distributed test, but it is at least covers different continents and different availability zones, and did reveal some interesting things. So we sent requests every hour to monitor the availability and status of these OCSP responders for about 4 months, and we were able to analyze around 50 million OCSP responses. There are 3 main observations from this. Yep. So April to September, this is continuing, and we will be monitoring and uploading data every month or so, I guess in perpetuity for this research study. So this resulted, in around 46 million. So this is the chart. You can see here we're starting the y-axis at 80. So it's probably a good chart depending how you think of things. But well, it turned out that the first observation is that we were actually never able to successfully receive requests for all OCSP responders in a given hour for any of the measurements. On average, 1.7% of requests failed. So we're not even into the 2 nines of availability with regard to our sample set, which we think is relatively representative of the web. And during the measurement period, there's at least 1 measurement that the client was never able to make a request to an OCSP responder, even though we sent 50 or so. So there's a couple spikes here and there. We'll dig into that right now. So yeah, here you go. 29 responders, or at least 1 that failed. Okay, geographical differences. You might see the different colors here. Some of these ended up being fixed because we told the OCSP responders that something was going funky, but the failure rate varies across the different locations. The average rate was between 2.2% in our Virginia data center, AWS East, and 5.7% from Sao Paulo in Brazil. So one of the interesting angles is digitalcertvalidation.com. This was a specific example. During the first 3 months of our measurement periods, the measurement in Sao Paulo could not get any responses from this OCSP responder, which serves actually the Wells Fargo certificate. So after we contacted them, they fixed that's this chart, right? This spike right here. The issue was fixed on August 31st. So yes, there you go. It was 404 for that entire period right there, until it was fixed. All right, so availability, transient failure. That's this blob right here on the left. Sometimes OCSP responders that serve OCSP responses for a large percentage of the web would just go down. So we observed that some were temporarily down for at least a few hours, even multiple days in some circumstances. So this is an example, our April 25th. This actually only happened from the measurements in Seoul, Sydney, and Oregon, which are all in the Asia Pacific region. And this turned out to be due to OCSP servers maintained by Komodo and Komodo CA, which I believe they just changed the name of their CA this week after an acquisition. But yeah, so all OCSP respective servers were not served. And interestingly, we also observed that some OCSP servers that are related to Komodo were also down. For example, Gandhi and a number of other providers actually CNAME to OCSP Komodo CA. And these other CA providers are just provided by by Komodo. So all of these went down, and that's your spike down to 90-some%. So what's the impact of the web? So how did this outage really affect OCSP Online? So if popular OCSP responders experience an outage, it could be a serious problem because so many certificates actually rely on OCSP, and the clients will not be able to check. So to measure this impact, we estimated how many popular websites from the, say, Alexa Top Million were unable to fetch fresh OCSP responses due to this specific outage. And this is the result. So we observed a couple spikes during our measurement period, which means that many popular sites were unable to fetch OCSP responses during that time. So these spikes were due to single OCSP servers going online. So this is, you're looking at tens of thousands of sites out of the top million at these cases. So this Komodo is down for 2 hours. Start SSL is down, OCSP Certum, Digicert were down. This is, some of these CAs are very popular and used by lots and lots and lots of different sites. So availability, OCSP, this is a general conclusion. OCSP responders are not fully reliable. There's reasons you can kind of intuit as to why that is the case, and we'll kind of get to that in the end. So the second thing that we measured here, and you can see that we're down, the y-axis actually is a lot lower in this case, and we're you can barely see it, but the validity of the response, this is, you know, pretty okay. So let's see how many OCSP responses have successfully received are actually valid. The OCSP responses can be wrong due to multiple reasons. The most representative ones are the format is not ASN1, which happened sometimes, or the serial number of the OCSP response is different from the OCSP request, or sometimes the signature was not valid. There were a lot of different ways that this can go wrong, and we saw them all. So here's the result. Generally, most of the responses are valid, but we often see the consistent error from some OCSP responders, which returns only 0. That's the red line here, around 2%. So mostly valid, but there are some specific errors. Okay, so the last thing that we looked into here was consistency. CRL is, I guess, widely used as well. So OCSP versus CRL, let's see if they return the same results. Which one is correct? We know that CRLs and OCSP responders should return consistent results. If it's revoked here, it should be revoked there. All right, so to measure this consistency, we need to obtain CRLs and so we went to the Alexa Top Million again, and we only used the certificates that supported both OCSP and CRLs, and we extracted the CRLs. And so from this process, we were able to extract 1,500 CRLs, which contained 2 million serial numbers for revoked certificates. And before asking the revocation status of the serial numbers, first we eliminated, so we went to the ones that were both OCSP and CRL, got the list, got the ones with the OCSP. Some of these were expired, so we just eliminate the ones that were expired and cross-check with census. And we filter this down, and we end up with around 700,000 or so unexpired serial numbers derived from CRL lists that we could check the OCSP from. So what's the expectation? This should be that every single one that was in the CRLs should return revoked when checking from OCSP. And this turned out to not be the case. There's, at least for all of these CAs right here, Start SSL, Covadis, Firma, returned good for CA certificates that were definitely revoked. And there were other situations in which it was marked as unknown. So we actually contacted the responsible CAs to report this along with their data set and measurement results, and asked them the reasons why. And the main reply was that these are 2 different platforms and synchronized by some sort of database triggers, and these were failing in some circumstances. So they were not using a consistent data store to mark certificates as expired, which is should give you pause when thinking about revoking a certificate. Okay, after we contacted them, they told us they would fix the issue. All right, web servers. So we did CAs. Let's step a next step down the ecosystem chain to web servers. A web server that's OCSP must stable compliant should fetch the OCSP response and cache it and serve it during its full validity period, and they should handle errors. And if they're unable to successfully fetch the OCSP, they should probably use a previous one as long as it's not expired. That's the expectation. Is you're a server, do your best to serve this OCSP. And so we took a look at some of the popular ones. This is not a very comprehensive survey, but it at least validated what makes up over 50% of the web servers online. So performance, we see that web server proactively fetches OCSP responses. If web servers do not prefetch OCSP responses and fetch them on demand, then you can be unnecessary latency. So it's kind of the latency problem in reverse. Rather than the client having to fetch OCSP and check, it's you connect to the server and the server connects it, fetches OCSP. This is unnecessary latency. From a caching perspective, you have to remove expired things from the cache. This is just what you should do in any sort of caching situation. And the third is availability. Web servers should periodically ask for fresh OCSPs before they expire. This is just the only way that this is ever going to work. Right. So how do we think they did? This is well, prefetching OCSP responses. Neither Nginx nor Apache does this, which means that the very first connection to a server that runs Apache or Nginx that has OCSP will not serve you an OCSP response. In fact, they don't block because the performance delay, but instead they do kind of what browsers do in that they just send off an asynchronous request to go fetch them. We found that they both cached the OCSP response, and Apache did not respect the next update in the cache, so it did keep around some old OCSP responses, whereas Nginx did fetch it. And you know, if there is an OCSP response on an error, this is something else that we found that was slightly lacking in the Apache web server. Okay, so we did CAs, we did websites. Let's move on to the last piece of the ecosystem, browsers. Whoops. All right, so to support OCSP must stable, there's three things. You need to understand the extension, present the certificate status request extension, and then reject the certificate if the response is not provided. And so basically, this is the methodology, request it, see if it rejects it. And also we check if it sends an additional OCSP response, just in case. So you probably, if you have an OCSP must stable certificate, you probably don't want to also fetch OCSP because then you lose all the privacy guarantees as well as potentially the latency guarantees. Okay, so first, we tested multiple browsers as well, multiple mobile browsers. First, we noticed that all of them are asking for the stapled responses, which is good. This means that all of these support OCSP stapling. However, we did observe that only Firefox displays a certificate error message if the user has a stapled OCSP response that doesn't come. So sadly, all the other browsers simply just accept the certificate and don't send their own OCSP response or really just don't do any OCSP checking at all after this point. So these results indicate that the clients are not largely ready for OCSP must staple. In fact, barely, they don't respect the OCSP must staple extension at all. And generally, most browsers don't do OCSP to any capacity at all. They request OCSP responses, but they don't respect this extension. So clients are largely not ready, and that's kind of the additional coding work is likely not too significant, but it's worth thinking through why
browsers haven't invested in this technology yet. Okay, so in conclusion, on the bright side, only a few players need to take action to make it possible for web servers to begin relying on certificates with OCSP must stable, but every single piece of the ecosystem needs to make a change. So the OCSP servers need to be more reliable. Web server software needs to do a better job of, or needs to be capable of consistently serving OCSP responses and handling web server failures and expiring their cache and doing all these sort of things. And then only then, once servers actually support this fully, do browsers can be updated to support OCSP must stable. We're almost at the end, so I'll take the questions.
I'll just make it very brief. I just want to point out that you looked at your popular web servers. It doesn't quite match up with sort of the origins for a lot of popular web content. That CDNs are the origin, so their support for doing the OCSP prefetch and caching and stuff like that is probably going to have a big effect on what's actually sort of the bits that are sent over the internet.
Yep, and that's a good point. And that's another part that I didn't. It's covered in the paper, but not in this presentation. That we did look at some major sites about what they do and major providers. And part of the motivation for this study was the work that I did at Cloudflare to make the service available, make OCSP must stable possible, and all the weird error failure cases that we made sort of led to the study. But yeah, so let me just continue with the rest of the conclusions. Yeah, so only a few players need to make action to make this to make it possible to enable OCSP must stable. The web server software, as I mentioned, it's possible to do this. It's possible to have a reliable server that does OCSP must stable. Sometimes it might require a slightly more complicated infrastructure to keep these in sync. There's questions about whether the web server should have external HTTP access or whether it should be preloaded with configuration. There are some questions about this, but I don't think these are insurmountable problems. So I guess the general conclusions is that there are problems all over here, but they're in the small percentage range, and a much wider deployment of OCSP must stable is, I guess the result of the study is that we think it's a realistic and achievable goal, but not today, but sometime soon. So the data is available at securepki.org, and this is still measuring. We're going to publish every month or so new data, and it's there should be a /IMC 2018. So this is research that was presented at IMC this year, and so that's sort of it. All right, so I'd like to thank the group for inviting me here to present this work and open up the floor for any questions.
Maarten Aartsen and CSCNL. So for the measurements you did for the availability of the OCSP responders, was that including the potential for caching or excluding?
So we did two things. There is a feature in OCSP that lets you do cache busting, essentially. Mm-hmm. So we measured both cached and uncached, and that data is in the paper.
Okay, so can you comment on the effect on the like the outage spikes you pointed to in the slides? Yeah,
the outage spike, it was the cache busting version of OCSP. So specifically Komodo and some of these other ones are using CDNs in front to cache them, and that would mask a lot of this specific issue. But yeah, so that's another reason that to be optimistic, right? Is that mm-hmm. if these failures do happen, they're less impactful because of how much caching is typically used by these OCSP responders.
Still not great that they're not available, but hey.
That's right. I mean, if the CDN caches it for 7 days, you can cover up a pretty big outage, but that's also not reliable.
Or the web server, right? That serves the actual OCSP response.
Or the web server, but you could imagine a scenario where you're scaling your web server and spinning new things up, and you don't have a cached copy, and yeah, it depends on the architecture.
Max Park, Cable Labs. Great work. I love it. Have you looked into many environment today? We're deploying, devices with certificates, which we need to verify the revocation. It's very important. So it's outside the browser space most of the time, but it's the same architecture, TLS to the cloud, and validate the certificates, right? Today, as far as I understand, most of these device certificates that are deployed, they completely ignore their revocation, but at some point we will have to do it. Are you planning or expanding your work to see if the fetching all these, because at this point it would be on the server side, right? The client would do the stapling, but they have to actually fetch these OCSP responses themselves. And one of the problems that I've seen in many environments that these devices might not be able to reach the OCSP because of network limitations. One of the things that we looked into, it was to support other distribution mechanism for these OCSP responses, because to make sure that they are closer to where these devices are, so they can fetch them and staple them, or just fetch them by themselves if the server doesn't staple properly. Do you think that in adding some other mechanism to distribute these OCSP responses might help the situation where you have outages that one mechanism might not work and the other might work? So for example, the proposal was to use DNS to distribute this not as an alternative to stapling, but as an alternative method to fetch this information that you can actually put in the stapling. Do you think that this might help the situation?
So just to clarify, you're talking about a situation where you have devices and then other devices acting as the server, or are you talking about revoking client certificates on devices?
Both.
Right. This work is, it is mainly focused on web servers and servers that are handled on the web. But in a lot of these IoT scenarios, you're talking to a centralized server, so these results still apply. With respect to making it easier for servers in a traditional context to get copies of the OCSP, we saw that over HTTP, it's not entirely reliable to do so. I tend to think that if must staple becomes something that people are attempting to deploy, that it'll be more likely that these OCSP responders will invest in having more reliability. It's not that hard of a service to really run, but it kind of would make sense to put it in DNS or some other mechanism to just have another place to obtain it. I mean, it has a specific lifetime. When it comes to actually clients having to demonstrate revocation on the client certificate, I have not thought that through very much, but it comes with the same caveats that if they can find it somewhere, they can use it. But is OCSP must staple ready for client certificates? I don't think we're anywhere near that case, and I think that's.
No, I totally agree with what you're saying. But
we need to wrap this up. We're over time already. So.
Okay, thank you.
Very brief or offline.
Offline is fine.
Thank you very much.
Okay, thank you.
Thank you. Thank you all the speakers. Thank you, Chris, for taking notes. And see you next time. Thank you. Sorry for the last one. What didn't work, it was